In Chapter 6, Part 3, Quantum Numbers and Orbitals, we're going to start to discover where the electron lives. So we left off in the last video with the idea that with the Heisenberg uncertainty principle, we could either know where it was or how fast it was going. So in 1926, Schrödinger proposes his famous wave equation. And so this equation is written H psi equals E psi. And so it does look like you could just cancel out the psi functions and basically have H equals E. So that is not true, and it turns out that these are something called a wave function. Where the wave function part of that is this psi part, the pitchforky looking thing. And so the wave function is a complex equation giving insight into the location. And so in order for this quantum mechanics and the H psi equals E psi equation to work, he kind of needed to simplify this down. So he started to treat the electron like a standing wave. And you may have heard of something called a particle in a box. So basically he set it up to where the particle must live inside the box. And then we have our different energy states, n equals 1, n equals 2, n equals 3. And so what he figures out is that as a particle in a box, he encounters these nodes in some of these. And so basically a node is a place where the energy is 0. So there are one node here, 2 nodes, and 0 nodes. So if you play a musical instrument, you can change the tone of something by changing how long the string is. We see this to be true also when we talk about looking at standing waves or the particle in a box. Basically, that in these allowed values, there are places where you see the energy and places where you don't see the energy. So a wave function, or psi, relative to the nucleus is described, the wave function tells us about where the electron is relative to the nucleus. Alone, the wave function is worthless. It doesn't tell us a whole lot. But if we square the wave function, it's going to give us the probability. So what is the likelihood of it being in any given location? So for any orbital, psi squared shows the probability of locating an electron at any given location. So we can get something called a probability density, which basically tells us where are we most likely to find the electron. So if we're most likely to find it, and this is all relative to the nucleus. And so if you were to think about the hydrogen atom on a 3D X, Y, Z scale, what you'll start to see is that the psi squared, which looks kind of like a particle dot plot, looks something like a sphere. So psi squared is a 3D sphere. And so this tells us basically where could we find the electron. So just because we can say something is X number of angstroms away from the center, what does that actually mean? Like, how far is that? And so when we think about the electron within an atom needs to have a specific area where it's expected to arrive. And so when we think about addresses, we have usually your address is composed of a street number, a street, a state, a city, those are out of order, and a zip code. All of that together will get you your mail. If you just put the street, it's not very specific. If you just say Florida, it's not very specific. So these are the specific directions to get you to any address. And so these 4 quantum numbers, so these 4 values are quantum numbers. And they give us insight into where the electron is. And so in the next couple of minutes, in the next several slides, we're going to talk about each one individually. So one of the first things that Schrödinger noted is that his equations determined that there were allowed values for n. So n really can equal any number from 1, 2, 3, all the way up to infinity. So this is one of the first things he solved. And so this allows him to describe, so Schrödinger is the first one to predict orbitals. That's nice, predicts orbitals. And so these orbitals show the locations or the distance from the nucleus. Where is the probability of finding an electron? So the first quantum number is the principal quantum number. You could think about this like this state. In the United States, there are 50 states. This principal quantum number is the most broad region. And so as we look at this image over here, we can see that if the green thing is our nucleus, we can see that the shells move out one at a time. And so each n is a principal quantum number. And so the allowed values are for n are 1 all the way to infinity. So any whole number, basically 1 or greater. And these are the discrete levels at which the electrons are allowed. So I like to think about this as the state. And so the next one is the angular momentum quantum number. And so the angular quantum number defines the type of orbital. And so as you move away from the nucleus, there are more orbitals. So the number of orbitals allowed increases as the distance from the nucleus increases. So L, the allowed values for L are 0, 1, all the way up to n minus 1. So that means if n equals 1, the allowed values of L are just 0. So for n equals 5, the allowed values would be 0, 1, 2, 3, 4. Now these are the allowed values. But it turns out that for the angular quantum number, it's important to note that the value of L corresponds to a specific orbital. Now we haven't really talked about what the orbitals are, so as we do that in a little while, you'll want to come back and review this. But for an electron in the s orbital, L equals 0. P, L equals 1. D, L equals 2. And F, L equals 3. Just because there are allowed values doesn't mean that the electron can have more than one L value. And that's an important concept as we think about this. So the first one told us where it was, in what state. This I think of a little bit more as the city. And so it turns out that in our states, there are only a couple of allowed values. So the big cities, there are only a couple. So the next quantum number is the magnetic quantum number. And so this determines the number of subshells within an orbital. And so the number of subshells, the allowed values, are from negative L all the way through 0 to positive L. Whoops, we'll just call that positive L. So if we look at this graphic, so for an s orbital, L equals 0. For a p orbital, L equals 1. So what you can see is that for an s orbital, we only are allowed m sub L also equals 0, because negative 0 through 0 to 0 is still just 0. But for the L equals 4, which is not on here, your m sub L values would be negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. So the allowed values are negative L, including 0 to positive L. And this is the number of subshells within an orbital. So as we start to, in a second, we're going to put this into a picture, and we're going to start to think about where specifically do the electrons go. So together, the quantum numbers are going to start to tell us where it is. So this is going to be a street address. So your electron is on Main Street, or it's on UNF Drive. There are lots of streets in lots of states, and it's possible that the street could be in multiple states or not. So together, these three values give an address to the location of an electron within an atom. In the same N, they're in a specific electron shell. Each subshell contains the electron in a given N and L. So some quantum number guidelines. In a shell with the principal quantum number N, it has exactly N subshells. Each subshell has a specific number of orbitals, 2L plus 1. And the total number of orbitals in a given shell is N squared. So my guess is right now you're kind of trying to put together what do these quantum numbers mean. And so I know that quantum numbers feels really complicated right now. But in just a second, we're going to basically turn over another sheet of paper and it's going to all fit together. So before we can think about where the electrons go, we want to think about what does an electron orbital look like. And so we're going to start with the s orbital. So the s orbital is probably the simplest orbital. And if you draw a Cartesian plot, or basically an x, y, z plot, it's a circle. So the s orbital is a sphere. And so it turns out that in 3D space, if this is our nucleus, it forms basically a sphere around the nucleus. And so when we look at this, it looks like a sphere. So this is our first orbital. Then we have the p orbital. And so there are 3 p orbitals. So the s orbital is L equals 0 and m sub L equals 0. For the p orbital, L equals 1 and m sub L equals -1, 0, and 1. And so this tells us that there are 3 p orbitals. And those 3 p orbitals, we will draw them all together and then separate. So you have one on the y-axis, you have one on the x-axis, and then this one's the hardest to draw, so I'll try to bold it out. We have one on the z-axis. So all together, it looks like a mess. But let's go ahead and look at what it would look like if we drew each of them kind of independently. So we could actually see what they look like. So as we look at these 3 orbitals, we'll go ahead and label them all the same. So if we think about the px, that p orbital is going to be located on the x-axis. Py is going to be located on the y-axis, and pz is located on the z-axis. So what we can see is they're all different, they're all separate, but they look kind of like dumbbells. And so aside from the fact that if we look at this hot mess of them all mixed together, but we could describe values, and in other chemistry courses, the m sub L's do specifically correspond to the x, y, or z p orbital. But what we can see is that for the s orbital, we have a sphere. In the p orbital, or for L equals 1, there are 3 suborbitals. So there are 3 p orbitals. So next we have the d orbitals and the f orbitals. So we'll start with the d orbitals. So the d orbitals, so in this case, L equals 2, which means that m sub L equals -2, -1, 0, 1, and 2. And so in this case, that tells us that there are 5 different orbitals. And when we look at this graphic, we can see that they all look different. Now, it is not important for you to know how to draw these or to really know what they look like. But what we know is that there are 5 different places where the electrons could go. So let's look at something a little bit more exciting. In the f orbitals, so for an f electron, L equals 3. So m sub L equals -3, -2, -1, 0, 1, 2, 3. So there are 7 different m sub L values, and there are 7 different orbitals pictured here. So what we can see is that the m sub L specifically corresponds to the number of different orbitals that compose a type of orbital. So you should start to be able to kind of see that the quantum numbers fit together. So we can have n, which tells you how far away you are from the nucleus. Then you have an orbital type, which is L. So you could be in the s, p, d, f orbital. And then you have m sub L, which tells you the specific place that you are in any given orbital. So as we start to think about this, we've said that there are electrons, and these electrons live in orbitals. And when we think about hydrogen, hydrogen only has 1 electron. So all elements other than hydrogen, all 117 of them, have more than 1 electron. So if you have more than 1 electron, where do they live? So 2 electrons fit in each orbital. Well, maybe not orbitals, plural. But each orbital only holds 2 electrons. So 2 electrons at a time can fit in any given orbital. So a p orbital, px, holds 2 electrons. The s orbital holds 2 electrons. And so the question is, if there are 2 people that reside in the same apartment or in the same building, we need a way how to tell those apart. We also want to start to think about what it means if there are 3 p orbitals. So we know that we have px, py, and pz. And so these 3 orbitals are all at the same energy. And this means that what we're going to call them is degenerate, meaning they have the same energy. So if you were to draw an energy diagram, they would all end up next to one another, which is different than an s orbital that would be at a lower energy. So when we think about the energy, as you increase the L quantum number, they're going to go slightly up, but every n value is going to move to a next level. And so they're all at roughly the same energy. And so if we have 2 electrons that are going to go in any of these orbitals, 2 electrons go in. So we need a way how to distinguish between these 2 electrons. So if there's electron 1, oops, that should be a negative sign, and electron 2, how can we tell them apart in any given orbital? So this comes to our last quantum number. The last quantum number is the magnetic spin quantum number, ms, or m sub s. So our last quantum number, m sub s, which is the magnetic spin quantum number, is going to allow us to tell them apart. And so this is going to tell us that our 2 electrons spin in opposite directions. So they are anti-parallel. So electrons spin anti-parallel. And so in this case, what we're going to see is that you have a positive spin and a negative spin. And so the Pauli exclusion principle states, no 2 electrons in the same atom can have the same set of quantum numbers. And m sub s differentiates between these 2 electrons. So in this case, what it's really going to say is that we can tell the difference if we go back to our graphic before. -1 or 1 and 2, this one would have a +1/2 spin and this one will have a -1/2 spin. So when we think about the quantum numbers, these four numbers together are going to tell us where the electron lives at the end of the day. So to review, our four quantum numbers are n, the principal quantum number, and as n increases, the electron is further from the nucleus. L is the angular momentum quantum number. This gives the number of subshells within the shell, or the type of orbital. And so the m sub L gives the orientation of the orbital in space. M sub S gives the direction of the electron spin. So if we were to draw an energy diagram where energy increases, we can have the n equals 1 state, n equals 2, and n equals 3. There are more states than this, but in n equals 1, we're going to have the s equals 0, and in there, m sub L equals 0. At n equals 2, we have L equals 0, which is our s orbital. We also have L equals 1, which is going to end up being our p orbital. In this case, we have m sub L equals -1, 0, and 1, which tells us that there are 3 p orbitals. In the n equals 3 state, we have L equals 0, 1, and 2. For the s orbital, this looks the same, so does the p, but the L equals 2, m sub L equals -2, -1, 0, 1, and 2. And so we can see those. And as we increase the number of electrons in here, we're going to start to see a spread to where for n equals 2, the L equals 0 or the s orbital is going to be slightly less in energy than the p orbital that is slightly higher in energy than this. So let's think about how we can use this information. So if an orbital has n equals 4 and m sub L equals 1, what are the possible values for L? So in this case, let's take this apart. So if n equals 4, the allowed values for L are 0, 1, 2, and 3. We know that m sub L definitely equals 1. So that tells us that the allowed values for L in this case are going to equal 1, 2, and 3. Because for L equals 0, m sub L only equals 0. For L equals 1, m sub L equals -1, 0, and 1. So that the final answer to that is 1, 2, and 3. So what is the designation for the subshell n equals 5, L equals 1? Well, the L equals 1 tells us that it's a p orbital. So this would be the 5p orbital. And so then we want to know how many orbitals are found in the n equals 4 shell. So the number of orbitals is n squared, which in this case would be 16. So the other ways that we can use quantum numbers, instead of just deciding how many there are, what do they look like, is we can determine the 4 quantum numbers for an electron in any one of these orbitals. So the important key fact is that the number of quantum numbers could change based on what we're learning about the electron. So in this case, n equals 3. L, because it's a p orbital, is going to equal 1. M sub L, we know that the electron is in the p orbital, but we don't know which one. So in fact, we don't have a value here. And because we don't know where it is, M sub S is also blank. So let's think about the 4dxy orbital. In this case, n equals 4, L equals 2. Because it tells us this designation right here that tells us where it is, m sub L could be any of the allowed values. in my class, you just need to pick one. Today, I'm feeling quite positive. I'm going to pick number 1. Now, m sub s could be either plus 1/2 or minus 1/2. You just get to pick one. So in this case, I'm going to pick plus 1/2. For quantum numbers, in my course, you just need to pick one. The n and the l are usually specified, but the other two are selected. If quantum numbers are exciting and you want to learn more about them, there are other courses in the chemistry department where you can learn that there are specifics. And there are specific, m sub l does mean something specific. But for now, we just need to pick an allowed value. So let's look at 5s. N equals 5, L equals 0, m sub l equals 0, and m sub s, in this case, I'm going to say it's negative 1/2 because I just wanted to pick something different. So when I ask for the 4 quantum numbers, you just need to provide any of the 4 quantum numbers. Not all of the allowed values, just what they are for this value.